Okay, we are now recording for 110 Acoustics, Unit 5, I believe it is, Pitch and Loudness. And the idea was to basically get that particular unit done. We are fast winding down toward the end of this course. Unit 6 that we'll cover next week takes only 1 week, and it's on masking, the upward spread of masking. And that kind of dovetails with what we looked at in 120, anatomy, where we talked about the weird shape of the traveling wave in the cochlea. So that's how these two courses gel together. So where were we last week? If I look at what my summary is from what we did, we began Unit 5, Pitch and Loudness, and we talked about fawns, and then we talked about mells, and then we began the topic about frequency resolution, and that's kind of where we'll pick up now. So if I go to share screen here, and look at our particular, can you see this particular picture here? Good.
Yes, got it.
All right, and where we will begin really is frequency resolution. And that kind of deals with, even in Unit 4, a week or so ago, I say 2 weeks ago, when we looked at difference Lyman, or just noticeable difference for frequency and intensity. In other words, differential threshold. You already hear something, but what's the smallest change you need to make for you to recognize or see a change or hear a change? And that's what you call frequency resolution. It's the ability to distinguish between frequencies close together. How's your fine tuning, in other words? Can you tell the difference between 1,000 hertz and 1,001 hertz? Or did I need to make it 1,010 hertz for you to notice a difference? And that's what happens with hair cell damage in the cochlea, sensory neural loss, which is also why speech word recognition gets poorer with sensory neural loss. So under the topic of frequency resolution, basically, the frequency discrimination, like I'm highlighting, is the ability to detect changes in frequencies. And when you're looking at thresholds in Unit 4 began with this particular discussion. What's the smallest change you need in order to recognize a difference? All right, frequency resolution, the ability of your auditory system to resolve or distinguish between the individual components of a complex sound. And it gets worse with sensory neural loss and damage to the outer hair cells. And so if I show a picture of a traveling wave, and you've got it seen there, and if I go to one earlier one, this is a traveling wave in a cochlea, and at the base of the cochlea you're hearing high frequencies, and at the apex you'd be hearing lows. The cochlea, as we know, is tonotopic, and you can see this orange flopping thing here, and it happens to be, pretend you've got hair cells all along it. Follow my cursor, one row of inner hair cells all along here, and then 3 rows of outer hair cells along the base, 4 rows of outer hair cells in the middle, and 5 rows of outer hair cells toward the apex. And remember, this is exactly the opposite of what you'd think. At the narrow tip of the cochlea, the scala media is widest. And we're only looking at the floor now, the basilar membrane, the floor upon which the hair cells stand. And in this particular case, this person is hearing a low frequency because the peak of the wave is toward the apex. So these hair cells are giving rise to stimulation of the 8th nerve and sending that information to the brain. Now this is what von Bekkesee, the discoverer of the traveling wave, found in his research. And so yes, like Helmholtz before him, he concluded that the cochlea is tonotopic. Specific frequencies are represented in specific places. And lows would be more toward the apex because, hey, that part of the basilar membrane is going to resonate with low frequency sounds because it's got more mass and less stiffness. Whereas the base of the cochlea has less mass and more stiffness, so it will resonate with highs. And so high frequencies will cause a traveling wave that will occur near the base, and low frequencies will cause one that occurs near the apex. Now, with outer hair cells, you can see the twofold action here. And see how this course dovetails with 120 anatomy, because this is almost exactly what I talked about last week in 120. Look at the blackened sharpness in this picture compared to this one. The outer hair cells are amplifying the traveling wave, making it taller, and they're sharpening the traveling wave. So this guy can distinguish between frequencies close together, whereas this person here cannot. And that's just kind of like a visual idea. And if you carry on and look at this summary picture, the blue here would be a traveling wave near the apex. The orange would be the envelope of that wave and showing you how it's shaped like a kite. It's very asymmetrical. And the steeper portion faces the apex of the cochlea. The shallow slopes toward the base of the cochlea, and the outer hair cell action, that sharpening and amplifying, that dual action of the outer hair cells. Now, with hearing aids, we can imitate one of those functions. I mean, we can imitate amplification specifically for soft sounds, because that's where this action is really taking place with soft inputs. The outer hair cells help the inner hair cells pick up sounds below 50 dB. The inners can't pick up 30 and 20 and 10. They need the mechanical help of the outer hair cells to do that. And so when we look at our situation here and the particular slide that I may have shown you last week, and we'll look at it again here, the action of these outer hair cells, look at the way they are moving, shrinking, okay? And when they shrink, they pull that tectorial blue membrane down so that it can shear or bend the hairs of the inner hair cells. This action serves to sharpen the peak of a traveling wave. So the outer hair cells die first because they are the moving part in the cochlea. The outer hair cells give rise to specific amplification of soft sounds, and that is why hearing aids today tend to focus on amplification of soft sounds. And you will learn next year that's called compression. Hearing aids use compression. And what does that mean in English? They focus amplifying soft sounds. If you start to talk loudly into the hearing aid, it automatically backs off. If you're talking softly, it works to amplify. So the focus of amplification of today's hearing aids is generally for soft inputs below 50, so that we can electronically imitate what the outer hair cells used to do. They're trying to imitate outer hair cell action. So when we go back to sharing slides again, here you are. If we move ahead here, you will see that here's a person with on the top. This person has two traveling waves. His cochlea is unrolled, okay, and he's got two peaks. So he's hearing two frequencies that are fairly close together. He can easily distinguish the difference between the two. With hair cell damage, you're looking at the middle panel. First, the peaks are smaller, and second, the sharpness is gone. So with hearing aids, you are able to restore one of those functions. You can make the waves bigger again, but the sharpness is gone. And that is why hearing aids for ears aren't like glasses for eyes. This is the point we need to drive home for us at Ozarks, because as clinicians, no, we're not explaining this to our clients, but we need to understand the situation so that we can better counsel our clients as to realistic expectations of hearing aids, knowing the limitations of hearing aids, so that they walk out of the office with realistic expectations. And counseling and explanation goes such a long ways. So when we now go to our notes, what do we have here? Place theory. Put a star by that. Place theory is Helmholtz. Helmholtz said specific frequencies are represented in specific places. Lows are represented at the apex, highs are represented at the base. The place theory. Okay? And that's the most easily recognizable theory of pitch perception. So that's usually how we describe pitch perception. Okay, specific frequencies represented in specific places. The cochlea is tonotopic. And traveling waves, I'm highlighting here, show how the cochlea is tonotopic. And here, traveling wave peak stimulates particular hair cells in a particular cochlear region. The traveling wave envelope here, I'm highlighting, is asymmetrical, like a kite. Outer hair cells, there you go. Put a star by that puppy. They amplify the traveling wave, especially for soft inputs, and they sharpen the peak of the traveling wave. Now, if you follow my cursor here, you're going to find out that this tonotopicness continues up the auditory system. Whoops, here's the eighth, look at the eighth nerve as it's leaving the cochlea. So these are all eighth nerve fibers. There's thousands and thousands of them. In other words, the eighth nerve has 30,000 fibers, like a rope. Okay? A rope is of many, many tiny twisted fibers. In fact, if we have 3,000 inner hair cells in each cochlea, each inner hair cell is in contact with 10 eighth nerve fibers. So 3,000 times 10 is 30,000. So look at how the eighth nerve is tonotopic as well. The fibers on the outside are high-frequency fibers. The fibers on the inside of the nerve are low-frequency fibers. And you can see that in this picture highlighted. So the eighth nerve also is tonotopic. And many people describe the eighth nerve in terms of tuning curves. Now you can think about these kind of like traveling waves in a way, but they're not, okay? Let's just take a look at this one here, for example. You got frequency along the horizontal. And the vertical represents decibels required to get some specific fiber to fire. So let's pick on this fiber right here. We'll just pick one of these fibers. Ding, take that one. How many decibels did we need to stimulate that fiber to get it to send information to the brain? At some particular frequency, we didn't need much. Okay, so that's going to be that neuron fiber's favorite firing frequency. And if we try to stimulate that nerve fiber with a lower frequency, we need more decibels to get that nerve fiber to fire. So here you're looking at 6 tuning curves, and they're probably representing 6 of these fibers. All in all, just to tell you, or to tell us, that the eighth nerve, like the cochlea, is tonotopic. But enough on that. Let's look at our notes here. Tuning curves show how the eighth nerve is also tonotopic. High frequencies on the outside, low frequency fibers on the inside. There's your numbers. Eighth nerve has 30,000 fibers, 10 from each of the 3,000 inner hair cells. Tuning curves represent the favorite firing frequency of any one of the eighth nerve fibers. They show the intensity required to get any specific eighth nerve fiber to fire. Note how they too are asymmetrical, just like the traveling wave is asymmetrical. And look at what happens with hair cell damage. The red. Here you might have some particular fiber of the eighth nerve, and the black tuning curve would describe it. One particular frequency gets that fiber to fire, and other frequencies you need way more intensity to get that fiber to fire. With hair cell damage, you're looking at the red. You need more energy, more decibels, more intensity to get that neuron fiber to fire. But looky, look at how round it is. So it means lots of frequencies around the favorite firing frequency can get that neuron fiber to fire. Okay? Carefully look at the verbiage of the vertical axis, the intensity required to make some specific eighth nerve fiber to fire. So with sensory neural hearing loss, not only are your traveling waves broadened and rounded and no longer sharpened, but also your tuning curves are broadened and rounded and are no longer sharp. And all of this is to tell us that hearing aids and people mix like oil and water, because the damage to the end organ of hearing is so vastly different from the damage to the end organ of vision. Hearing and vision. Again, vision, conductive vision loss. Hearing, sensory neural hearing loss. So really what you're getting is, if we say tuning curves from outer hair cell damage are broadened, just as the traveling wave is more rounded. It shows poorer frequency resolution. Now, we won't spend much on the bottom part of this, but I'll just introduce you to a guy named Rutherford. Okay? Rutherford had a different theory of pitch perception. And he said, now a lot of this stuff, this is what I want you to look at, this sentence. He said, you know how you tell pitch? It's not so much the place theory. That's sort of it. It's the number of times that the eighth nerve fires per second. It's the number of times that the eighth nerve fibers fire per second. What does that mean? Well, he said, listen to a motorbike. When you're hearing it rev, each is exactly the same, an explosion of white noise. How come when it revs, your pitch perception goes up? And it's the, if you hear that quicker, your pitch perception goes up. So he said to himself, it's not so much the place where the hair cells, it's the rate of eighth nerve fibers firing per second. And then you think, well, Rutherford, I don't know about you, because nerves can't fire more than 500 times a second. They can't fire more than 5. So how do you tell the pitch of a 2,000 hertz tone? So he goes, well, that's where they happen in volleys. One will fire at twice a second, and the other one's firing at 500 times a second, and 2 times 5 is 1,000. It's kind of like, okay, Rutherford, all I can say to you is this. The place theory enjoys much more popularity, but the Rutherford temporal firing theory is there to explain things that the place theory can't explain. Okay, and it's there to explain what the place theory can't explain. There's a couple of weird little things here. If I look at this particular picture, let's see if we can find this guy here. If I got it or not. Not 100% sure if I do. I doubt it. Nonetheless, another one is called the, oh yeah, here it is. There, I just saw it. There we go. Now look at these two tones. The top one is a complex sound. The bottom one's a complex sound. Okay? But what's different about the bottom one is, look, they took away the fundamental frequency. And you know what you're still going to hear? The overall pitch of this tone is going to be around 200 hertz, because all these are 200 hertz apart. And even if you take away the fundamental frequency, you're still going to hear an overall pitch of 200 hertz. And they call that the case of the missing fundamental. Okay? That's better explained by Rutherford's temporal firing rate theory than by the place theory. Same with the motorbike revving. That's called periodicity pitch. So there's two phenomena. Okay, the case of the missing fundamental, and the second one is periodicity pitch, the motorbike revving. Those two phenomena are not well explained by Helmholtz's place theory. That's why Rutherford's theory does still exist. The real fact of the matter is they probably both help us determine the pitch of a tone. Albeit, I think the place theory has more of a contribution than the temporal theory. But what you're learning here is actually quite advanced audiology. People getting their AUD degrees at university study this stuff. We won't go any further in it. I just wanted to mention what they are, mention that there are two different theories for pitch perception and mention that the most common one is the place theory, but also the Rutherford is the name associated with the temporal theory, and it is still there because it explains a couple of phenomena that are not well explained by the place theory. There you have it in a nutshell, and I'll be done with that. Let us move on and go to the next page of our notes. So we will. So all of this stuff here is kind of like, you can read it, but it's kind of more for FNO, for nerds only, or freak not out. It's what I've said verbally here is the take-home message we should have. So here's the two odd things about pitch perception that are not well explained by the place theory. The case of the missing fundamental and periodicity pitch. Okay, so have a read of that yourselves and just make a note on your notes that this is Rutherford's theory, and these two phenomena are better explained by his theory than by the place theory. Very good. Now we can summarize. Look at this. Wow, done pretty good here. All we've got is this stuff here toward the bottom of the page. Let's look at some typical psychoacoustic results with sensory neural loss. Number one, loudness and recruitment. Put a star by that. Let's talk about what that is, and we'll show you in a picture. Loudness and growth and recruitment. There we go, right here. Have a look at this particular slide. This is one that's very commonly shown all around in fields of hearing loss. Look at the horizontal axis. It could represent dB-SPL, it could represent dB-HL, doesn't matter. Okay, it represents decibels. And the vertical axis represents psychoacoustic perceptions of intensity. So the horizontal represents intensity in decibels, and the vertical represents your loudness perception. So the horizontal is physics, the vertical is psychoacoustics. So now look at normal loudness growth, the 45-degree angle line. To a normal hearing person, 10 or 20 decibels sounds very soft. To a normal hearing person, 50 or 60 sounds comfortable. And to a normal hearing person, 90 to 100 begins to sound too loud. Now let's go and damage your hair cells. If we go in and ruin your outer hair cells, so now you can't hear sounds below 50. So look at the more steep line. That's impaired loudness growth. So let's follow where my cursor is. If I circle 50 or 60, now 60 sounds very soft. And yet 100 sounds too loud. That's called, this where I'm circling here is called recruitment. It's where the two lines meet. And it's in plain English, it means that those with sensory neural hearing loss have very similar loudness tolerances as people with normal hearing. So if you yell in a hearing impaired person's ear, it's going to bother that person just as much as it bothers someone with normal hearing. 100 decibels is going to sound just as loud to someone with sensory neural loss as it is to someone with normal hearing. The difference is sensory neural loss, most of it can't hear below 50 because the outer hair cells are damaged. So when you've got outer hair cell damage, you have an inability to hear soft sounds below 50. And so you've got a loudness growth function that looks like the impaired loudness growth. And literally, we use loudness growth, that word, okay? Like a seed into a sapling into a tree, okay? How fast did it grow from being an infant to being of old age? How fast did the loudness grow from being just audible to being, whoa, too loud? With normal hearing, my hands are far apart. I've got a big dynamic range. The top is 100, the bottom one is 0. With sensory neural loss, I've done this. Now I can't hear till 50, and yet 100 hasn't moved. That's what I'm talking about. The dynamic range of hearing is diminished. Now, if you think of conductive hearing loss, that's like putting a plug in your ear. So when we put plugs in our ears because there's loud music, or we plug our ears so we don't have to hear the person next to us snoring at night, or we plug our ears because we're mowing the lawn, okay, and the noise is loud, we're giving ourselves a conductive hearing loss on purpose. We're doing it on purpose, okay? We're plugging up our ears. So when you plug up your ears, your whole room goes up. Think of this, the elevator, the whole box goes up. The floor and the ceiling go up because I've got an ear plugged with wax, or I have an ear plugged with otitis media, or I have an ear plugged with otosclerosis, or cholesteatoma. Any one of the middle ear pathologies acts like a plug in the ear. So always think of conductive hearing loss as a plug in your ear. And that means your loudness tolerance is going to go higher, and your floor of hearing sensitivity is going to go higher. Both, the floor and the ceiling. With sensory neural loss, there's nothing wrong with the middle ear. There's nothing wrong with the outer ear. So guess what? You have no mechanical blockage of sound getting into the ear. What you have is hair cell damage, mostly outer hair cell damage, and now you can't hear sounds below 50. That's why most people have mild to moderate sensory neural hearing loss, because most people have damage to outer hair cells, and outer hair cells die before inners because outer hair cells are the moving part, and in the moving part in any system is going to wear out first. So in a CD player, what's the first thing going to go? The CD player. The next thing that's going to go is the speakers. The last thing that's going to go is the amplifier, because it's not moving. The moving part dies first. So outers tend to die before inners. So outer hair cell pathology gives you what is called a sensory hearing loss. And put that in quotes, sensory. Sensory means mild to moderate in degree and good speech recognition in quiet. Not bad. 80%, not bad. Okay? On the other hand, sensory neural loss. The second half of that word, neural, means damage to inner hair cells. And that usually is preceded by damage to outers. So neural loss is usually more severe in degree. And what do inner hair cells do? They send sound info to your brain. So with damaged inner hair cells, you've got a garbled message being sent to your brain. So with neural inner hair cell damage, you've got a severe degree of loss and markedly poorer speech recognition. There you go. These are two camps of sensory neural loss. Sensory versus neural. Okay, and back to our notes now. Let's see what we got here. Looking at this here, where are we? Loudness, growth, and recruitment for the common binaural, sloping, high-frequency sensory neural loss. The thresholds increase. The floor is elevated. Loudness tolerance. The ceiling remains similar to normal. Recruitment. As a result, loudness grows more rapidly than normal. From being barely audible to being too loud is only a distance of 50 dB. From 50, it's barely audible, to 100, it's too loud. Implications for hearing aids. Compression. There's that word. Specifically, wide dynamic range compression. And what does this do? It amplifies soft sounds by a lot. If you'll see the arrows here, soft sounds are amplified by a lot, and loud sounds are amplified by little or nothing at all. In other words, it's a hearing aid that focuses on amplifying soft input sounds. The focus is on the floor. The focus is trying to imitate outer hair cells, taking a narrow dynamic, a normally wide dynamic range, and squishing it into a smaller one. So if you look at this picture here, here's hearing loss on an audiogram. High frequency hearing loss. You can see the zeros or the O's are at around 50 or 60. And now if you look at the right, you're looking at the curves, because now this right graph is in dB SPL, whereas the left graph is in dB HL. And remember what we said 2 weeks ago? The bottom, to see this curve, this bottom blue curve, that's minimal audible pressure. The softest it took to hear all the different frequencies with one ear under a headphone. And remember a week or so ago, 2 weeks ago, we said that is capital I, capital S, underline, bold-faced, italics. That is 0 dB HL. So that bottom blue curve is the top line here. Okay, 0. Now, if you've got hearing loss plotted going down on an audiogram, this is what it would look like in dB SPL. The guy's hearing loss on the left would look like this if plotted in dB SPL. And notice how his floor has gone up in the high frequencies and his ceiling has remained unchanged. So this guy's dynamic range is only about 50, whereas the normal dynamic range is around 100. So this picture is showing you the same thing as this picture. The only difference is that this picture is showing you frequency, whereas this picture is not including frequency. Okay, so this one's just a further extension, but it's showing you again narrower dynamic range compression. So here's what a hearing aid would have to do. It would have to take soft sounds and whoop them up to here. But loud sounds wouldn't amplify them at all. Okay, you will learn more about this in your course next year called 240, compression, hearing aid compression. And the sad thing for you is, hang on here. The sad thing for you is that, and I'll stop sharing for a second, you'll have to be using this book called Compression for Clinicians by me. So it's a textbook that is commonly used, and it's all describing outer, inner hair cell, types of compression for different types of hearing loss. So break down the word sensory neural into sensory and neural. Sensory involves outer hair cell damage, neural involves inner. Okay, share screen again, and we will now look at our notes. Implications for hearing aids. Circuit has to amplify soft sounds by a lot and loud sounds by little or nothing at all. Effects for speech. Vowels remain audible while consonants do not. So if we look at this particular picture here, there you go. Normal hearing shown on the top. The X's and O's are all around 0 or 10. Hearing loss, typical presbycusis. This would be sensory loss. Good hearing in the lows, moderate hearing loss in the highs, leaving one with an inability to hear the high frequency consonants. So the rounded traveling waves caused by damage to the outer hair cells is mostly going to be found at the base of the cochlea. And you know how I always describe that as? When you think of a room and you think of a doorway in the room, where does the carpet get the dirtiest? Right at the doorway. That's why you have a mat. So all sounds, everything is activating the high frequency hair cells in order to get to the apex. Everything is good. The traveling waves are all going through the base. So they're either stopping at the base, or they're going through the base and stopping at the middle, or they're going through the base and stopping at the apex. I like to just make an analogy that's why we tend to have trouble hearing treble. Okay, it's the floor is always being moved by any traveling wave. You've got to go through the base to get anywhere else in the cochlea. So that's my little analogy of it, but we tend to lose high frequency hearing first. And that shows here. The vowel sounds are audible, and all letters of speech that use the larynx. So anything that you're holding your throat, Z, V, J, M, D, B, and all your vowels, N, M. But as soon as you're starting to get ch, sh, k, they are not only softer, okay, but they are also higher pitched. Basically, the trouble hearing treble. All right, and this picture is showing you normal frequency resolution. Think of the cochlea as being tonotopic, like keys on a piano. And now you've got poorer frequency resolution. The keys on your piano just got fatter. Okay? You haven't got the fine tuning anymore. And that's largely because of hair cell damage. Taking this home, loss of frequency resolution due to outer hair cell damage. Both the traveling waves and eighth nerve tuning curves become wider and more shallow. More on this in next unit of masking. The person cannot distinguish between frequencies close together. Can't separate speech from background noise as well. And this is the major complaint of hearing aids and hearing aid wearers. Background noise. They can't separate frequencies close together. They have a loss of just noticeable difference in frequency. In other words, their differential threshold has gotten worse. And since we had the time to look at it, I'm just going to direct our attention back to this one picture here, just so we can look at it. Here, this is a picture of frequency resolution. FNO, freak not out, just look at the fact that the lines go up. Okay, now let me explain this picture. Here's frequency, low on the left, 1,000 in the middle, 10,000 on the right. Now look at the vertical, and you get that triangle, delta F. In other words, what's the difference threshold for frequency? How much of a difference did I need to make for the person to notice that there was a difference? Okay, now you got a bunch of lines here, and all they mean is at 5 dB, 10 dB, 20, 80, whatever. Look at the big picture. Forget the different lines. Look at the fact that for the lows to the mids, you don't need much difference in frequency for you to recognize that there's a difference. But when we get to the very high frequencies, you can see we need to make a bigger difference in order to recognize that there was a difference. And this is for normal hearing people. If you take outer hair cell damage and here and ruin the outer hair cells from where they used to be like this, well, now, Houston, you've got a big problem because you haven't got this sharpening action taking place by the outer hair cells, and now your traveling waves, instead of being sharp, are now dull. So this was what von Beckersey discovered in his cadavers in the basement of Harvard University. Dead people have dead hair cells. The year was 1945 to 1949. They didn't have what we've got to look at things. And he would have to stimulate the cadaver's head with 120 decibels to see traveling waves. But his traveling waves were all dull and rounded, because dead people have dead hair cells. He didn't get that sharpening of the traveling wave. He couldn't see that happening. We only discovered this some 20 to 30 years ago. The year was 1990, and that's when we began to distinguish, that's when we began to distinguish the differences, okay, between outer and inner hair cells, what they do, what the differences are. Okay. Basically, that takes us to the very end of our Unit 5. Any questions? How's it going, Karen?
Okay.
Good. Great. All right. So I will soon sign off here. I'll grab myself a morning coffee, and in about, I don't know, let's see, it's about, at about 11:30 Central Time, I'll log in for 1:20. And we'll look more at cochlear physiology, which deals a lot with what we were talking about here. Here we were saying, what's the psychoacoustic implications of the hair cell damage? And you necessarily have to describe that kind of damage to some degree, and you're looking at the net result. But the purpose here is really to describe how, with your clients, you need to understand that the damage in the inner ear is permanent. And your job as a hearing instrument specialist is then to counsel appropriately about the limitations of hearing aids so that people walk out of the office with realistic expectations of the hearing aids. Because if we don't do that, the devil of hearing aids is going to nip us in the rear end. That client is going to be back, and she's going to be back. And because we didn't take the time at the beginning to explain things. I always say to people, I can't make your hearing normal again, but I can't make the hearing like when you were 10, but I can turn the clock back 10 years. Okay, it's a hearing aid.
Right.
And that's very important. So, okay, great stuff. It's been a slice. Thanks always, Karen, for showing up. It's always great not to have to talk into an empty computer screen. I will stop recording here, and we'll talk to you later, okay?
Okay, see you shortly.
You bet.
Bye-bye.
Bye.